Okay? Spin cannot be 0, spin cannot be 2. Spin has to be 1. Clear? Now, how to give mass to the weak gauge bosons without breaking the phase symmetry of the Lagrangian? So that is the question. Okay. The answer is the Higgs mechanism. Higgs took a clue from one observation, it's a simple observation. You see, the scalar mass term is invariant under phase transformation because phi star phi is even invariant. Clear? Clear? It remains invariant under phase transformation not only for positive mu square but even for negative mu square. Negative mu square is imaginary mass. Imaginary mass can have other problem, but it has not problem with phase transformation. Negative mu square phi star phi will again remain. Okay? Okay? So what he did, he assumed mu square to be clear. Then you plot the scalar potential, which is mu square phi star phi plus lambda by 2 phi star phi whole square. So you plot it as a function of the complex field. Suppose this is the real axis and this is the imaginary axis, and the z direction is b. Okay? Okay? So you see that at the origin b has to be 0, but at very tiny non-zero phi, quadratic term will be larger than the quartic term. It is the epsilon square will be larger than epsilon fourth. Okay? So that means if mu square is negative, then of course it will be start from 0 then become negative. But at larger phi, the quartic will win, so it will again becomes positive. Okay? So if you excuse a clumsy drawing by me, so this should roughly look like this type of the potential. Yes or no? Okay. So the minimum will occur when the first derivative vanishes. Okay. So let's calculate first derivative. So if I look at the first derivative, I am taking derivative along the real axis. Okay? So this phi, I am taking after along phi r. So this is phi r square, this will be phi r to the power 4th. So I will have twice mu square phi plus twice lambda phi cube equal to 0. So that's why I put the factor of half there. So that will occur at phi equal to minus mu square over the okay. So the minimum of the potential energy is occurring not for the zero value of the field but finite value of the field, which is called V, vacuum acceptation value. Because by definition vacuum corresponds to the minimum of the potential energy. Okay? The minimum energy level, which is by definition vacuum, of course not from zero value of the field but finite value. Clear? That is a very important thing. Just internalize that. Okay? If you look closely, the size of this shape of the potential looks like the bottom of a wine bottle. Yes or no? This is a very useful analogy because if you have a because the shape of the bottle maps the shape of the gravitational potential energy. If there is a drop of wine, it will not sit here. It will fall to a point on the rim because that is the stable minimum, that is the energy minimum. Okay? Here. Now let us contrast this with the usual case of with mu square greater than. Then you see the quadratic term is positive, quadratic term is positive. So it will look like you start with the origin, but then both are positive term. So it will look instead of looking like bottom of a wine bottle, it will look like the top of a wine glass. Okay? That's again a very useful analogy because the shape of the glass maps the shape of the gravitational potential. If there is a drop of wine left here, it will sit at the origin because that is the ground state, that is the potential energy minimum. Okay? You can shake the glass a little and study the motion of the wine drop as small oscillation problem around a stable minimum. Okay? Goldstein chapter 6. Okay? You can do the same thing here, but of course for that you have to translate the origin scale by this constant scale V, because automatic expansion is stable around a energy minimum, not around a energy maximum. Okay? That means the real part of the potential you translate by this constant amount V, and this fluctuation around this point you describe as the physical scalar filtrage. Clear? Clear? So any perturbative field theory you have to do making this translation of scale. Clear or not? If you do that, then you say miracle happens. You write this as the constant A plus x field Hx. Here the same thing, because we are considering the real part. So I shall the same. So you are getting a quadratic term in A mu whose coefficients is E square B square. Okay? You did not put any mass term by hand, but you got a mass term through back door. Okay? So your gauge field has a mass equal to E density. Clear? What about the physical scalar field H? You can make the same transformation here. Actually, this will be V plus H whole square. Okay, and this will be V plus H whole fourth. Then you look at the coefficient of H square term. Okay, coefficient of the H square term will give you MH. It will be minus mu square. Mu square is negative, so the physical field will get a real mass. Okay? Okay? You can do this exercise at homework. Okay, it will not take more than 5 minutes. Okay? I think you will get a factor of 2 there. Okay? So from this equation, this should be equal to okay, mu square will be root lambda times B, simply using this equation. Now V from this equation is the gauge boson mass divided by the gauge coupling. Okay, so if you use this one, then it will get root 2 lambda upon gauge coupling times the gauge boson mass. Okay, so the physical Higgs boson mass will be the physical gauge boson mass times self-coupling upon gauge coupling. You know how much is the gauge coupling. These are measured quantity. Okay, it's 0.5 or 0.6, something like that. You do not know the self-coupling, but for perturbation theory to be valid, you know that the self-coupling must be less than 1. So there is an upper bound. Okay? Okay? Simple, so you get an upper bound on the Higgs boson mass, which will be of the same order as the WZ boson mass. Okay? Which is of the order of. Okay. So we expect to see this particle are the large hadron collider.
But then the symmetry is broken, right?
Sorry?
Under the phase transformation.
Sorry?
Under the phase transformation, then the symmetry is broken.
Yeah.
In this case, right?
Yes. That is the most important point. Okay? So let us try to observe that point. Let us see what we have. Let us try to summarize what we have done so far. Okay? If we had a positive mu square, which is the usual case, then the ground state will occur at zero field. Okay? Now, if you have zero field, by any phase, it remains 0. So ground state will possess the phase symmetry of the Lagrangian. Okay? So you cannot get mass. When you make mu square negative, the ground state came to a finite value of V. When you make a phase transformation, it went around the rim of the bottom of the bottle. So it is not remain phase invariant. Okay? Okay? These phenomena where the symmetry of the Lagrangian is not shared by the ground state is called spontaneous symmetry. Okay? And in these phenomena which allowed you the ground state to have a non-zero vacuum accretion value gave mass to the gauge bosons through that door. In fact, if you look here, the gauge bosons are getting a mass through their gauge interaction with the background Higgs field V present in the vacuum. It is possible not only quantum mechanically but even classically, because V is a constant field. Its space-time derivative are 0, so it is not carrying any energy momentum. It is only carrying the gauge charge. Of course, gauge charge is not spontaneously broken, electric charge is not, but this is an analogy. It is carrying weak isospin. That weak isospin is spontaneously broken. Okay, so that is for what is given mass. Okay, so the weak gauge bosons are getting their mass from their gauge interaction with the background Higgs field which is present in the vacuum. Clear? Clear to everybody or not? So we can now go for the slideshow.
Slideshow.
You have to bring this down. You have to bring this screen down. But as they are arranging for the slideshow, any question you ask, any question you any question.
What is small m and capital M? What is the relation?
Capital M is the gauge boson mass, small m is the Higgs boson mass. When you do this exercise, if you make the substitution here and the fourth power substitution here, then you expand it, you look at what is the h square term coefficient. H square term coefficient will precisely give you this. Okay, you do that exercise at home.
I mean, this mathematics works out, not because of the sign of mu square per se, but because of the relative sign of mu and lambda.
No, it may appear that, but it is actually the sign of mu square. It is actually the sign of mu square. It may appear that, but it is actually sign of mu square.
Okay, no, so my question is that for fermionic fields, we cannot write terms like trilinear in fermions or quartic fermion fields because of dimensional reasons. Now, if we could have written those terms, then
Why don't you discuss it after?
Okay.
This is not directly. It is not.
Okay,
It's
okay.
not that I am saying something you don't understand. I want to restrict question to something that I have said you don't understand.
Okay.
Other questions we can discuss after, because the focus will be lost.
uh,
Okay. So why LHC? We need LHC to look for the Higgs boson. I have already done this on board starting from the electromagnetic Lagrangian. Clear? I am simply repeating what I have done on board. Okay? So this was the phase transformation which demanded the gauge particle to be massless. Okay? Okay? But then we did spontaneous symmetry weighting. Okay? Okay? And then we got a mass term through that door. Okay? We got a mass term for the gauge